So we're starting our course on robotics with a lecture about space, about how do you reason about space. And this is not specific to robot arms or mobile robots. It's critical for robotics in general. Because ultimately, robotics is the science of physical machines operating in space. It's not about bits on a hard drive, on a wire. Ultimately, robotics, you get to the metal, you get to something that moves in physical space. So how to reason about where things are in space is very important in robotics. So what we cover here today is the beginning of the course. It applies to everything else that we do. One note is that the material we cover here also applies to other fields where you have to reason about space, 3D space, 2D space, computer graphics, for example. Everything we cover here today, you'll also find if you're taking a computer graphics class. Some conventions might be different in other fields, but it's the same conceptual items. So let's think about 3D space. And as an example, consider a robot arm that's about to execute a grasping task. Maybe you know where the target is in the world. And in general, you always have what we call a reference frame for the world. So somewhere you have decided by convention that, hey, this is where my reference frame for the world is. Maybe it's somewhere down here. This is a coordinate frame that is my reference for the world. Okay? And you have your x, y, and z axes. You know, somehow, maybe a sensor, you have a camera that does object detection, you know where the target, where the glass is with respect to this coordinate frame. You also know where the end effector of the robot is with respect to the same coordinate frame. But in order to execute this task, the robot needs to know where the target is relative to itself. It's not enough to know where everything is relative to your base coordinate frame. You need to be able to compute where things are relative to each other. And this is the basics of what we are going to cover in this lecture. Similarly, if you have a mobile robot and you have knowledge of a map that tells you where the obstacles are in the world, it's not enough for your mobile robot to know where the obstacles are relative to some base coordinate frame. A mobile robot needs to know where the obstacles are relative to itself. So you need to have this ability to think about space, but to also reason about multiple coordinate frames and move between different coordinate frames. And this is exactly what we are going to cover here. So let's formalize the notion of space, position in space, from a mathematical perspective. Let's start with two-dimensional spaces, which are easier. In Cartesian spaces, then, the location of a point P is determined by the vector P, which has two components, which you can think of as projections along the x and the y axis. So the vector P and its projection along x, its projection along y. Okay? We always write these as column vectors. Always positions are column vectors. If it's just to save space, we will often, however, also write them as transpose rows. Exactly the same thing. But you always have to remember that formally correct the vectors locations, vectors that denote positions and locations, are written as column vectors. So in 2D space, this vector is a two-dimensional vector. It has two components. If we were in three-dimensional space, then obviously we would have three components, px, py, and pz. So now P is a vector living in a three-dimensional space, same as writing it like this. Okay. But the one thing that is important to remember is that we don't have a single coordinate frame. So here we're showing one coordinate frame and the position of the vector P in that coordinate frame. In robotics, there are numerous coordinate frames. There is a coordinate frame for the robot, a coordinate frame for the room, a coordinate frame for the end effector, many coordinate frames. So we have to keep track which coordinate frame we're talking about at any given point. So to do that, we will generally use, in this course, capital letters to name the coordinate frames. And to make it clear that now we're talking about the point P expressed in coordinate frame A. So we have the vector PA, and the components px, py, and so forth are still relative to coordinate frame A. We can have many coordinate frames. But still, these are nothing more than two-dimensional vectors. These are three-dimensional vectors. And as such, we can perform on them any operations that we've learned in linear algebra. Multiplications, dot products, cross products, multiplications with matrices. And we will make heavy use of all that in this lecture. So here's an example of when we would have multiple coordinate frames. So think here that you have a camera that's attached to a robot arm. And the camera is observing the location of something in the world. The camera tells you this is where a point of interest P lies. But of course, the camera will tell you where the point P is with respect to itself. So the camera knows, with respect to its own coordinate frame, which we name here B, where the location of the interest point is. So we know the location of P in the coordinate frame B. But maybe we'd like to know not where P is with respect to B, but where P is with respect to our base coordinate frame, which we've named here A. So the way that works is, if we know the transform that gets us from coordinate frame A to coordinate frame B, and we know where point P is in coordinate frame B, then we are able to compute the location of P in coordinate frame A. So let's formalize this. We have the location of point P in coordinate frame B that's given to us. The camera tells us that. So then, if we multiply that by the transform that goes from coordinate frame into coordinate frame B, the result of that will be point P expressed in coordinate frame A. And in a second, we will make it very concrete what this multiplication means and what this transform actually looks like from a mathematical perspective. But here is an item it's something specific to our notation, but it makes things a lot easier to remember, right? So you have the transform that goes from A to B, TAB, and you're multiplying that by a point expressed in coordinate frame B, and the result is that same point expressed in coordinate frame A. So it's easy to get these things confused. Wait a second, shouldn't this be the other way around? Shouldn't this be the transform that goes from B to A, right? Because ultimately we're taking PB and we are converting it into PA. So shouldn't T be the transform that goes from B to A? No, T is the transform that goes from A to B. And this is a convention that, if you remember, it'll make your life a lot easier as you deal with these transforms. One way to remember this convention is to use these superscripts and subscripts the way I use them here, right? So transform from A to B multiplied by P expressed in coordinate frame B gives you the point in coordinate frame A. So if you wish, abusing notation a little bit, these two cancel out. And in general, if you always write your points, your transforms, using a left superscript and a right subscript that tells you what coordinate frames you're dealing with. So for transform, you always have from a coordinate frame into another coordinate frame. For points, you have the coordinate frame that it's being expressed in. So if you follow this convention, then it'll immediately be very obvious when the chain isn't right. When, for example, if two of these subscript, superscript are not the same, it means you don't have the right chain of transforms and points. So bottom line here, transform from A to B times the point P in coordinate frame B gives you the same point P in coordinate frame A. So let's make this concrete. Note that we can chain these, right? So let's say that we have a point P that's observed by a camera in coordinate frame C. The camera is at the end of a robot that has at the base coordinate frame B, but then we have a different coordinate frame from the world, A. And we'd like to know the location of point P with respect to coordinate frame A. Again, the same rule applies. If we take the point expressed in coordinate frame C, we left multiply by the transform that gets us from B to C. And then we left multiply that again by the transform that gets us from A to B. The result of that is the same point P expressed in coordinate frame A. So again, transform from A to B times transform from B to C times the point in coordinate frame C gives us the point in coordinate frame A. Let's make this concrete.